Hey, physics students. This is the first lesson in a new unit here. This unit is going to be about energy. And over the course of this unit, we're going to learn about potential energy and kinetic energy. We're going to learn about conservation of energy. We're going to learn lots of stuff about energy. But this first lesson in the unit is about a concept called work. So we're going to talk about work. We're going to talk about what work is, when work is done, when work is not done, how to calculate how much work is done, and our target is to be able to describe the work done on an object. So let's go ahead and let's talk about work. Alright, when we use the word work in physics, we mean something a little bit different than when you use the word work in everyday life. Picture two teams of, what do they call it when they pull the rope? Tug-of-war. Two tug-of-war teams, and they're really evenly matched. They're both pulling on the rope and it's just not going anywhere. They're both pulling really, really hard in opposite directions and it's just not going anywhere. They're doing the tug of war. It's a really good match. It's not even moving, right? Okay. You might say that these tug of war people are working really hard. But in physics, in a physics sense, we would say they're not doing any work. Okay? Well, work is a force applied over a distance, is what it is, okay? So, when you apply a force to something, and it moves some distance under the influence of that force, then some kind of work has been done, okay? So, in order for work to be done, there needs to be two things. There needs to be a force applied to a thing, and it has to move some distance from where it started. There has to be a displacement, okay? If either one of those isn't there, no work has been done. When we talk about work, we use the variable W, just capital W for work, and the unit for work is a new kind of unit that we haven't seen before. The unit for work is called the joule, Joule, joule. It's named after a scientist whose name is James Joule in the 19th century, and joule is abbreviated with a capital J. Now we can calculate how much work is done to an object by taking the force that was applied to it times its displacement. So work is force times delta x. W equals F delta x. Work is force times displacement. Alright, consider the problem here. It took 50 joules to push a shopping cart 5 meters. With what force was the shopping cart pushed? Okay, so we can use our equation for work that we just discussed to solve this problem. So we said that the work is the force times the displacement. The problem here tells me that the work done was 50 joules. $50 joules of work. And it tells me the displacement was 5 meters. And it wants to know how much force. So I can take these numbers and I can put them into that equation right there. So let me go ahead, and the work was 50 joules. The force, we don't know. And the displacement was 5. So you can see, to solve the equation, all I have to do is divide both sides by 5. Force, 50 divided by 5, and 10. And then, of course, we measure force in newtons. And let's look at our significant digits. This number only had one significant digit, so I can only have one in my answer. 10 only has one significant digit. That 0 is not significant, unless I put a decimal point right there. Right. So we're good on significant digits. So the answer to the problem, the force, is 10 newtons. Okay, a couple of things to keep in mind about what we've just talked about here. First thing, we're kind of limiting ourselves to situations where the force and the displacement are kind of in the same direction, not at any kind of weird angles to each other. At weird angles, we would have to use some trigonometry to deal with that. So we're gonna limit ourselves to situations where the force and the displacement are in the same direction or in opposite directions. And speaking of opposite directions, the sign on work, whether it's positive or negative, is important. If your work is negative, then you can see either the force or the displacement would have to be negative. If your work is negative, one or the other is going to have to be positive, and the other one negative to make a negative work, right? Which means that the force and the displacement would be acting in opposite directions, which means the force would be acting against the motion of the object, right? So the sign on work, whether it's positive or negative, is an important thing to keep in mind. All right, so there's a little bit about the work as we use the word in physics, right? Work is force times displacement. We did a problem on that. Next time, we will go ahead and talk about energy. We'll talk about potential energy, and following that, we'll talk about kinetic energy. So hopefully that helps us to be able to describe the work done on an object. Till next time, take it easy.